started. Thank you, everybody, for joining us for another TigerStream. This month, we are joined by Amy Hurrigan with the USGS. Amy is a geologist with the U.S. Geological Survey in Nashville, Tennessee. She holds a Bachelor of Science in Environmental Science with a concentration in karst geology and water resources, and a Master of Science in Geoscience, where her thesis research focused on karst geochemistry. She earned both degrees at Western Kentucky University, go Tops. Her professional work involves a range of projects related to karst hydrology, groundwater quality, and Tennessee geology. She also has a high level of expertise in ArcGIS Pro, supporting spatial analysis and data visualization for geologic and hydrologic investigations. For those of you who are joining us at the end of this, we're going to have a Q&A session. So if you have any questions, put them through the Q&A. And then, without any further ado, Amy, floor is yours.
Awesome. Thanks, Matt. Thanks for having me. And thank you, everybody, for joining to watch my talk. I'm going to try to share my screen really quick. All right. My name is Amy Hurrigan, and I won't go into a whole lot about myself since Matt gave me such a great introduction. But I will say that most of my work at USGS currently focuses on karst hydrology, groundwater quality, and the geology of Tennessee. And today I'm going to talk about ambient groundwater quality and karst hydrology studies in Tennessee. So there are 3 projects that I'm going to discuss today. They are cooperative groundwater studies between the U.S. Geological Survey, or I'll say USGS, and the Tennessee Department of Environment and Conservation Division of Water Resources. And I'll refer to them throughout the rest of this talk as TDEC. So the projects that I'm going to talk about are characterizing the ambient groundwater quality of the principal aquifers of Tennessee, mapping karst groundwater flow paths for community drinking water springs, mapping groundwater flow and delineating recharge areas for major springs and caves in karst areas of high conservation value. Groundwater is a really important resource in Tennessee. 1.5 million people in 159 communities rely on groundwater for their source of drinking water. Groundwater is the main source of public supply in West Tennessee, and Memphis relies entirely on groundwater. Karst Springs supply public utilities to 55 communities and 11 non-communities in Middle and East Tennessee, and the USGS estimates that about 594,000 people in Tennessee self-supply with 100% groundwater, and that's from both wells and springs. The grand divisions of Tennessee are really important to mention. Those are official divisions designated by the state law, and they are in the state's constitution as well. The grand divisions officially are Western Tennessee, Middle Tennessee, and Eastern Tennessee. Sometimes we will shorten those to East Tennessee and West Tennessee. And this map shows the official counties and major cities that are in each of those grand divisions. West Tennessee has Memphis, Middle Tennessee has Nashville, and East Tennessee has Knoxville and Chattanooga. Now, the divisions are based on a lot of different factors, but the state's geology, hydrology, and physiographic characteristics play a really big part in the divisions. Another really important set of boundaries to discuss are shown on this map. This is the physiographic sections of Tennessee. West Tennessee is made up of the Mississippi alluvial plain and the East Gulf Coast plain. Middle Tennessee is the Highland Rim, which is sometimes divided into the Western and Eastern Highland Rim. And the Nashville Basin is in the middle of that. Sometimes that's referred to as the Central Basin, and that's actually the result of the erosion of the Nashville Dome. The Cumberland Plateau is to the east of that, and it lies in parts of Middle and East Tennessee. And the Sequatchie Valley is a 3 to 5 mile wide erosional valley that was cut into the Cumberland Plateau. As you move east, there's the Valley and Ridge, and east of that, the Blue Ridge region. And these are all part of a larger physiographic regions of the eastern United States. In this map, you can see the principal aquifers of Tennessee. West Tennessee has the alluvial and sand aquifers. Middle Tennessee is where you can find the carbonate aquifers of Silurian Devonian age and Mississippian age. The Pennsylvania sandstone aquifers are found on the Cumberland Plateau. And in the Valley and Ridge region, you have the Cambrian to Ordovician carbonate aquifers and the crystalline rock aquifers in the Blue Ridge region. This section, the cross section at the bottom, shows the vertical orientation of those principal aquifers. This map is from the Tennessee H2O report, and it shows the distribution of public water systems as point data. And the blue dots are public water systems that use wells for their supply, and the green dots are public water systems that use springs. So this is a really good visual representation of where and how groundwater is withdrawn from the state. Over in the west, the Mississippi embayment aquifer is the highest yielding aquifer in Tennessee, and public supply in this area is entirely wells, as you can see, and that's because of the deep sand aquifers here. In Middle and East Tennessee, you can see that there's a mix of wells and springs. And as you move to the east, the number of springs used for public supply increases. And you'll also notice there are some areas with no points at all, and there are some parts of Tennessee that do rely on surface water for their public supply. This figure shows the Mississippi embayment aquifer. It's one of Tennessee's most important aquifers. The Memphis sand aquifer of the Claiborne group is of tertiary age, and it underlies about 7,400 square miles of West Tennessee. The formation is generally a thick body of sand with alternating confining layers of sand and silt. And the Memphis sand ranges from about 0 to 900 feet in thickness. And the aquifer recharges in West Tennessee and parts of Mississippi, kind of on the right top side of this figure. And then the water reemerges to the west in the Mississippi River Valley alluvial aquifer near the Mississippi River. So water from this aquifer is considered generally old and also of high water quality. And the Memphis sand is the source of water for most wells in West Tennessee. So this map shows you the carbonate rock at or near the surface in many parts of Middle and East Tennessee. And the occurrence of these rocks often results in the development of karst features, and in some parts of the state results in really well-developed karst landscapes. And we did a little math with this shapefile and came up with a total of 43.5% of Tennessee is underlain by carbonates. And Tennessee is also the state with the most documented caves, just to point that out. So what you get when you have all that carbonate rock close to the surface is karst landscapes, like I mentioned. And so karst landscapes form in areas underlain by carbonates that are generally limestone, and they dissolve after extended contact with flowing water that's slightly acidic, generally naturally acidic. And so the solutional features that form are shown on this figure. Some of those are sinking streams, sinkholes, karst windows, caves, and springs, and those form when the conditions are conducive. So I want to point out that some of these features are what we refer to as recharge features. So the sinking stream and the sinkhole that has water flowing down at the bottom of it, those are recharge features, and those add water back into the ground. And then we also have features that we consider discharge features or resurgence features, like springs, and those allow the water to reemerge back at the surface. So in general, the broader questions that we're trying to answer with this body of work are: what are the ambient conditions of the groundwater? What are the flow path directions of the groundwater in karst areas? And what are the recharge areas for important springs and caves? All of these questions applied to Tennessee specifically. So the first project that I'm going to get into after giving you guys all that Tennessee background is about characterizing the ambient groundwater quality of the principal aquifers of Tennessee. So the objectives of this project are to design an ambient groundwater quality monitoring network and then sample the wells and springs in that network. I want to talk a little bit about the site selection. We attempted to distribute those sites among the different aquifers based on usage statistics. And then when it came to deciding whether to sample a well or spring, that decision was based off of common usage and accessibility to the aquifer in that specific area. And then efforts were also made to evenly distribute the sites spatially across the state and to avoid known contaminated areas because we were truly trying to capture ambient groundwater conditions. So after sampling the network, the data will be made easily available to both the public and TDEC. And after completion of this project, after the 5 years, we will produce a comprehensive report on the groundwater quality of the principal aquifers of the state. I want to mention the project chief for this project is Laura Rule-Whittle, and we do have a water quality specialist in our center at the USGS, which is Jim Kingsbury. And some of my colleagues that worked on this project were Christy Hill, Spencer Smith, and Michael Gratzer. So this is a 5-year project with projected ongoing sampling as a routine across this network once we have it established. And so the major aquifers that I mentioned earlier were divided into 4 geographic zones, excuse me, for sampling scheduling. Zone 1 was West Tennessee. Zone 2 was the Western Highland Rim and Central Basin. Zone 3 was the Eastern Highland Rim and the Cumberland Plateau. And Zone 4 was the Valley and Ridge and Blue Ridge regions of East Tennessee. During the first 4 years, we plan to sample 1 zone each year, leaving the 5th year for us to revisit the regions again and attempt to fill any gaps we may have spatially or within our data. And then it's projected that each site in a network will be resampled every 5 years. And as a part of the sampling program, we hope to sample 20 to 24 sites in each one of these zones with a 10% QA/QC sampling. So the constituents that we sampled for at all sites included pH, specific conductance, temperature, dissolved oxygen, alkalinity, major cations and ions, nutrients, trace elements, dissolved organic carbon, volatile organic compounds, and tritium. And at select sites, we sampled for pesticides, radon, radionuclides, total coliforms, and E. coli. And those select sites were based on site factors like site type, was it a well or a spring, and the depth of the well, factors like that. So since November of 2024, when we started sampling, we've sampled 67 sites in zones 1 through 3. This map shows you the distribution of those sampling sites. We've sampled 30 of 30 sites in zone 1, all of those being wells. We sampled 20 of 20 sites that we wanted to get in zone 2, which is the Western Highland Rim and Central Basin. 15 of those were wells and 5 were springs. In zone 3, we've sampled 17 of 22 sites in the Eastern Highland Rim and Cumberland Plateau. And in this zone, 5 were wells and 12 were springs. So you can kind of see the trend that I pointed out in the earlier slide. And then zone 4, we have sampled 0 of 24 so far, but we are projected to wrap up the end of zone 3 and move into zone 4 this year. So this is a map to show some very preliminary field results from each site that we sampled. And this shows specific conductance. And SC is we also call specific conductance SC. And that's a measure of how well the water can conduct electricity. And conductivity increases with increasing concentrations of these ions. And so it's an indirect measure of the presence of dissolved solids like chloride, nitrate, sulfate, phosphate, sodium, magnesium, calcium, iron. And this can also be an indicator of pollution, or in some cases, it can give indication to residence time in an aquifer. So the symbols on this map range from the smallest dots being 16 to 65 microsiemens per centimeter, and the largest dots being 560 to 980 microsiemens per centimeter. And what we can see, how we can use this data, this is a very basic example, but to characterize these aquifers and to characterize the water, we see that the lower numbers, the lower concentrations of SC are in the Mississippian embayment in the recharge area, so where the water just entered the ground. And then when you move over to the area where the water is resurging back out of those really deep aquifers, the SC is much higher. So that has likely had a lot more time in the aquifer to interact with the aquifer materials. And I also, as a Karst person, have to mention that there was a measurement of the 980 was in the Central Basin in those Ordovician carbonate aquifers. So that's another kind of insight that we can get from the SC. This is a close-up of the Mississippi River alluvial aquifer and the Mississippi embayment of West Tennessee. And this shows hardness results. And so again, what you can see in this, just taking a really quick look, is the hardness is less in the recharge zone, and it's higher once it's had time to interact with the materials in the aquifer, and it emerges back out on the surface. Another thing that we sampled for was tritium, and this map shows the results in West Tennessee. So estimates of groundwater age can be enhanced by sampling for tritium. It's a radioactive isotope of hydrogen, and it has a half-life of 12.32 years. So the concentration of tritium in results can help classify groundwater as modern, mixed, or postmodern. And that's based on the timeline is 1953, and it's related to nuclear testing. So typically, modern groundwater is more prevalent in shallow wells than deep wells, in fractured rock and carbonate aquifers compared to clastic aquifers, and in unconfined areas compared to confined areas, in humid climates, compared to arid climates. So results greater than 1 tritium unit represent modern water, while results less than 1 tritium unit suggest older groundwater. And this is an example, another example that supports the younger water and the older water, and some younger water coming back up. So in conclusion, for this project, we sampled 51 wells and we sampled 17 springs. So USGS analyzes, stores, and publicly serves this water quality data. And this is all going to be available on our online water quality databases. This QR code, if anyone wants to grab it, is the USGS water data for the nation. You can find historical and these data on this database. We will also publish regular data releases for this project, and those are available on sciencebase.gov. And then, like I mentioned earlier, at the end of this 5-year project, we will compile a comprehensive report on the groundwater quality of these principal aquifers. So the second project is mapping Karst groundwater flow paths for community drinking water springs in Tennessee. And this is a 5-year project to map groundwater flow paths and identify those recharge areas for selected communities. There were 4 years of field work and this final year for the preparation of an overall report. So I'm happy to report that the 4 years of field work are complete for this, and we are really getting near the end of the writing phase and getting ready to put the report for this into peer review. And there are multiple data releases for this project available online right now for anyone interested, and I'll bring those up at the end. This picture that you see is a fluorescein injection in Cowan, Tennessee. And this is a safe non-toxic dye that we use in the two projects I'm going to talk about for the rest of the time. And I do want to mention the project chief for this is Ben Miller out of Nashville. This map shows 66 public drinking water springs in Tennessee. There are 55 community springs and 11 non-community springs. And just to define what that means, TDEC defines any public utility spring with more than 100 connections to be considered a community spring. But some of these springs that were really high rated on our list had greater than 3,000 connections. So some of these are not small springs. Some of them were located in areas with population greater than 5,000. So some decent sized communities. When a public drinking water utility uses a spring as their source, they're required to submit a source water protection area. And I know if this is a stormwater group, you all are probably familiar with wellhead protection areas and things like that. So this is the same concept. SWPAs are delineated and submitted by these water utilities. It's their responsibility to do that. But if they don't have the skill or the ability to create this, they can request outside help. That can come from consulting agencies or TDEC or USGS. And at the end of the day, we do not draw their source water protection areas, but rather we help figure out the actual recharge area for their spring, give them the data, and then allow them to improve the accuracy of their source water protection area. There is really not a standardized method for these communities to create a source water protection area. Some of the methods are listed here in order of from the least to the most accurate shape produced. The left, you'll see an example of a wellhead protection area that I got from EPA.gov. And this is clearly a really simple shape, a geometric shape. This is a radius. But the example on the right is one for a spring. And this shape was created clearly using some additional information. It looks like they used, at the very least, the topography to help delineate this shape. But they did not do a hydrologic study to confirm if this was correct or not. So the method that we use is fluorescent dye tracing. And we will use that inside and outside of this area to help the communities confirm whether or not they're accurate. And then this data combined with other information like the topography or the geology can help produce a really accurate source water protection area. To select sites for this study, we created a rating system and listed all of those public community springs. And then a set of criteria was determined based on the shape of the source water protection area. Like, does it exist? Do they have one? Is it a geometric simple shape, or is it a more complex shape? Is the system a community or not a community? Is there well-developed karst in the area? What is the population? How many connections do they have? What is the average production of the spring? And so we considered all those criteria, rated those, and then totaled the score. And the highest scored springs were considered the most vulnerable. So using our system, 12 community springs were selected in 8 areas. And those were Van Lear and Mount Pleasant on the Western Highland Rim, Woodbury in the Central Basin, Lafayette in the northeastern Highland Rim, Cowan on the Highland Rim against the western escarpment of the Cumberland Plateau, Jasper, which is in the Sequatchie Valley against the eastern escarpment of the Cumberland Plateau, and Caryville and Morristown, which are both in the Valley and Ridge. And over 4 years, we injected dye into 106 separate features, and we monitored 324 separate sites. And I will explain what that means right now. So when we go into an area to start working, we perform a Karst hydrologic inventory. And during that time, we do intensive field work and recon in order to locate and document karst features. So we're specifically looking for sinking features with water flowing into them as potential injection sites, and springs and surface features to monitor for dye that might move through the water after an injection. This is the digital software that we use. Some of you all may be familiar with this Survey 123 and the companion app Field Maps we use heavily in these two projects. And then once we decide where our best injection sites are, we establish the monitoring network around that, and we're able to use this software to share these locations and photos and information with our coworkers. And then when we do a dye injection, this map shows some ideal injection sites. Sinking streams where 100% of the water goes underground, sinkholes with water flowing at the bottom, and a karst window with an opening exposing an underground stream. Those are all really great places for us to put our dye. And then some great monitoring sites on this graphic are flowing water in the cave and springs downstream from the injection sites. And so again, what we do is introduce a safe, non-toxic dye into these sink points or recharge features, and then we monitor the resurgent features with charcoal receptors. In this little video, this is a fluorescein dye injection that we did into a karst window, a really huge karst window in Morristown, Tennessee, and 100% of this water is going to sink at the end of this stream where you see. So we hope that water all goes down, that dye slug should go away within, generally depending on the discharge rate of the water, hours to days. That dye will be gone underground, and then we will hopefully pick that up on packets downstream. So these are the dye receptors. We also call them packets, and they contain activated charcoal. When they're placed in the water, dye absorbs to the material. And these are placed in the water on the surface and also sometimes in cave. And since dyes have different peaks on the color spectrum, we're able to monitor for multiple dyes simultaneously. So when we go out to do a dye injection, we'll say a round of dye injections because we are typically injecting 3 to 5 different dyes at a time. And so the dye will also not only absorb to the charcoal continually while it's in the water, but it absorbs cumulatively. So the longer the packets are in the water and the more dye that is in the water, the higher the concentrations should be on those results when we get them back from the lab. I also want to mention that we change packets at set intervals, and that allows us to bracket travel times of the dye. So we typically will change our packets out 48 hours, 1 week, 2 weeks, 4 weeks, and 8 weeks after the day that we put dye in the ground. And that allows us to see how long it takes dye to move to different features. And we also generally will try to change these packets out especially in important locations before we do a dye injection, and send those to the lab just to get a background line of any dye that may already be in the system. There typically is none, but that allows us to get a baseline and truly see if we're getting positive results. So in general, the methodology for this work was to establish a network of monitoring sites and injections, both inside and outside the source water protection area. And then once the dye is injected and packets are placed and collected and changed, they're shipped to the lab. When the results come back, we're able to draw dye paths between those injection points and the monitoring sites with straight lines. In a rare instance, we may have a cave map and we may have enough confirmation that a dye injection entered and exited the cave, and we can put that cave map in instead. But generally, we are only mapping point-to-point straight line flow path directions. So this looks pretty crazy. I'm going to put some really generalized arrows on here to explain what's going on this map. What you see with the blue arrows are several dye injections that we did. Some of those, I think 4 of those are outside the source water and protection area, and I think 4 of those were inside. I think there are 8 total there. And so that showed us, okay, these areas are recharge areas for this spring. And then you see all these other, injection points with lines going away. And that, although they didn't go to the spring we were really trying to trace, that gave us other important information, and that allowed us to draw a boundary. So we know somewhere between the arrow at the very top, the red arrow at the top, and these blue arrows, that's a boundary between 2 different watersheds, 2 different recharge areas. And so that the dye injections that go to this target spring, as well as dye injections that do not go, as long as we have established an adequate network that surrounds all of our injection sites, if we catch it, we can use that information to help us draw these recharge areas. And so this map shows the red outline is the source water protection area for this community. And then the light blue just shows what we confirmed are recharge areas for that spring. So accessing this data, we do have quite a bit available right now. You can search these on ScienceBase. You can Google these and they'll come up pretty easily too. But we do have water year 2022, 2023, and 2024 available. And 2025 is in the works. It'll be out really soon. And then with this project, like I said, we'll also have an overall report, a pretty thorough report, and that is nearing completion of the writing process now. So the last project that I want to talk about is mapping flow and delineating recharge areas in karst areas of high conservation value. And this is another 5-year project. And for this project, we used the suitability modeler in ArcGIS Pro to help identify study areas. Then once we identified those study areas, we performed those karst hydrologic inventories, established our networks. Then we performed dye injections, got our results back, mapped the groundwater flow paths, and delineated recharge areas. And of course, like all other work, this will be published for the public to access. So this photo is Virgin Falls, which is located in Scotts Gulf Wilderness Area State Park. And it is one of the main attractions to hikers at the park, although it's about a 9-mile round trip to get to this and back to your car. A very strenuous 9-mile hike. It's a really popular site. So we dyed Virgin Falls with fluorescein on St. Patrick's Day. And all of the water that you see in this waterfall, it's estimated this day was about 10,000 CFS. And all of this water emerges out of a cave up above this waterfall. It comes out of a cave, it flows over this waterfall edge, and it sinks directly in the hole that you see at the bottom. So it doesn't flow downstream at all. It comes out of the ground, goes over the waterfall, and goes back in the ground. So a really ideal injection site for us and a really pretty site for a lot of hikers on St. Patrick's Day. And one more thing I want to say about this is that little circle, that's my colleague, just for scale of how huge this waterfall is. Like I mentioned, Ben is the project chief on this also, and my colleague Elena Ornelas Crowley is also on this project. Much of Tennessee is underlain by Ordovician to Mississippian-aged limestones. And so I mentioned earlier, Tennessee has the highest documented number of caves in the United States, and that number is 13,600 as of the most recent update. And I promise there are still lots and lots more caves out there to find. Tennessee is the most biodiverse inland state, and it also has a really high degree of endemism. Karst systems are really important as hydrologic, geologic, biological, cultural, educational, and as a resource, a recreational resource. So it's really important to understand the hydrology in order to effectively conserve these areas and for resource management. So with Tennessee being, so important as an entire state, how do we figure out what areas to study? So I mentioned earlier the ArcGIS Pro suitability modeler, and that's what we use for site selection in this project. This flowchart kind of shows you how to move from your goal to your most suitable locations to study. And the goal for us was karst areas of high conservation value. Next, you organize or create your base criteria. For us, that was the geology, public lands, biodiversity, etc. And then next, you will derive data. If there are data that you need that do not exist, you may have to derive something. For us, we did have some cave data that didn't exist that we had to work with. And then you are going to transform and weight that criteria, and you'll end up producing a suitability map. And then from that, there's another tool that will pull locations out and give you, based on some parameters that you enter, give you the ideal locations for your study area. So although several rasters that we used were available, we had to come up with 3 specific rasters for this work. And those included cave density, stigobonts, and troglobonts. And what happened was we got special permission to obtain the data. These were point data, and we were able to take that data and aggregate it from point data to a 1 kilometer square grid. And then that data was able to obscure the precise cave locations. And I want to talk about just briefly, troglobonts are cave-dwelling critters. They live their entire lives underground. And stigobonts are a type of troglobonts that live strictly in the water in the cave. So these were 3 really important criteria for this. And so we wanted to be able to represent that. This map shows the cave density. Like I said earlier, we were able to obscure precise locations. The values in these cells range from 0 to 46 caves per square kilometer. Documented caves are really concentrated, as you see, on that western escarpment of the Cumberland Plateau. And the highest value on this raster was in White County, with 46 caves in a 1 kilometer square grid. So because cave obligate species are directly related to the precise cave locations, we had to do the similar method with both of these. And this map shows troglobonts. And the highest value was in Grundy County with 188 troglobonts per kilometer square. Same thing with our stigobonts. And those were, again, the highest value was in Grundy County with 145 species. I'm going to explain this suitability raster a little bit more detail. So after the input rasters are organized, they're added to this modeler and weighted against each other. And that's what you see in the far left. Those are the input rasters. And you, as the user, enter in the weights that you want to apply to that. And those are compared to just each other. And so this is a little subjective. So this is where knowledge and expertise in specific fields is important. After the rasters are weighted and entered into this model, then the data within each raster is classified and ranked from most suitable to least suitable. So this example is cave density, and it had an overall ranking of 10 among the other rasters. Rare and endangered species was another raster that was weighted as a 10. And what is produced by this step is a transformed raster where each cell is assigned a value, which represents the suitability for this specific criteria. And that's what you see in this red map. And you repeat this step for every single raster until you've ranked all the criteria within the raster. This is an example of a suitability map that was produced by the modeler. Each grid cell is 1 kilometer square. The area of darkest green are the karst areas of highest conservation value. The their highest value here is 324.5 in the darkest green, and the lowest is 54.5. The good thing about this tool is you do not have to visually inspect this and pick your areas based on like where are the dark green areas. You can use the location tool within the modeler, and it's going to pull out those locations. So this is an example of a locations map that was produced by the modeler, and there are a variety of different parameters that you can change and evaluation methods. This pop-up shows you some of the different criteria, some of the different parameters, I'm sorry, that you can edit to give you different results. And the evaluation methods are also really important. Those are the different statistical methods to produce your locations based on those values within those cells. And so this is a highest value map. The locations on here are also ranked from number 1 to number 10, with number 1 being the darkest green and number 1 also being the most suitable. So this is the map that we're using for this project. And these are the 10 locations that were extracted with the following parameters entered into those menus. We had a total area of 750 kilometers square between those 10 regions. We used the highest value method. We set our minimum area at 10 square kilometers and our max area at 75 square kilometers. And then we also set to have a 5-kilometer buffer between different areas. That's optional. You do not have to do that, but we didn't want all of our areas clumped in one spot. So the number 1 on this location is Scotts Gulf Wilderness Area State Park. And we have worked and actually completed work there now. Next is Wolf River near Pall Mall, which came up as number 3, and the Duck River, which came up as number 6. And we are currently working in both of those areas. Ben is leading the Wolf River and I'm leading the Duck River. And I also want to mention that we didn't completely leave out number 2 and number 4. Those are the Smoky Mountains and the Calf Killer River in Sparta, Tennessee, and those are both currently being studied or have been studied in other projects. So Scotts Gulf is on the Cumberland Plateau. It is over 10,000 acres, and it's surrounded by thousands of acres of land that's managed by other agencies, both government and NGO. The Caney Fork River in White County flows through the park, and most of the study area is underlain by a sequence of strata known as the Cumberland Plateau sequence. And this is an alternating sequence of strata that are soluble and confining. And those are the Pennington Formation, the Bangor Limestone, the Hartselle Formation, and the Mont Eagle Limestone. The plateau is capped by Pennsylvanian units, and most of the valley floors and under the Caney Fork are Mont Eagle limestone in this area. And these pictures are just some of the really cool features that form in the Cumberland Plateau. Very famous area for pits, as you see on the far right. These are photos from Scotts Gulf's grand opening in 2025. It is a brand new state park in Tennessee, and we were actually dye tracing it well before its official ribbon cutting. So Ben and I are both there at the ribbon cutting. I mentioned earlier, Virgin Falls is here in this park, and it's a main attraction. The Caney Fork River, the Caney Fork Trail, and lots of other caves, waterfalls, springs, mountains, and trails are in this area. From February of 2024 to December of 2025, we established 112 monitoring sites, and we injected 43 different features with dye. This project did require a lot of field work, and it was very physically demanding, a lot of backcountry backpacking. The field work and data collection for this project is complete now. And this map shows you some of those results. Again, I'll put some arrows here. These are really generalized. If I put an arrow for every line, it would be overwhelming. But you can start to see the flow of groundwater between injection sites and those springs. The next area was Wolf River near Pall Mall, Tennessee. This is also on the Cumberland Plateau. This area is underlain by St. Louis and Warsaw limestones in the valley floors. The ridges are made up of the Cumberland Plateau sequence, and the ridges are capped by Pennsylvanian-age units as well. There are many caves and other well-developed karst features in this area too. We started on the Wolf River in July of 2025, and this work is currently ongoing, and we were set to do a dye injection yesterday, actually, in this area, but we are all snowed in and stuck. So this will be another dye injection coming up in a few weeks. So far, we have 39 monitoring sites and 10 injections in the Wolf. Some preliminary results here just kind of show the flow of groundwater into some of these major springs and caves. Finally, the Duck River is in the Central Basin, and this area is covered in cedar glades and hardwood forests with some croplands. The Unali Wildlife Management Area is a 12,800 acre WMA with a high degree of biodiversity in both the flora and the fauna. The Duck River Complex State Natural Area is a 2,600 acre area within the WMA, and that is actually where our work is focused on right now. And this area is underlain by the Lebanon and Ridley limestones of the Stones River group of Ordovician age. The Duck has many well-developed caves and karst features. The river is among the most biodiverse waterway in North America. The watershed is home to 151 species of fish, 60 species of freshwater mussels, and 22 species of aquatic snails. We just started working in this area in December, just last month, and this work's ongoing. We've already established 27 monitoring sites just for our first 4 injections, and field work is going to be going on in this area for probably about another year. Let's see, and I'm going to put, these are very preliminary results that are from our week 1 and week 2 packet changes. So it will be a while before this data is available publicly since a lot of this is ongoing, but the suitability model will be a data release. You can access that and kind of see how we designed that model. And then we also are working on Scotts Gulf State Park dye tracing for a data release since we're finished with that. And then before I take questions, I'll explain this picture. This was a pit that was about 70 feet deep in the Duck River area. And there was a little water flowing at the bottom, but no water flowing in from the surface. So we filled a 50-gallon rain barrel with water, hooked it to a tractor, and took it out in the woods, and then put a hose down the pit and poured dye into the hose and then hooked the hose up to the 50-gallon tank and flushed the dye with 50 gallons of water. And that was a very, very fun and cool day. So that's all I have. If anyone has any questions, you can put that in the question and answers.
Well, thanks, Amy. That was an amazing presentation. Always love hearing about your work with USGS. For those of you who are listening and may have questions, there's a Q&A icon at the bottom of your screen. If you're on a mobile device, you might need to hit the three dots, depending on what kind of device you're using. But to start us off, Amy, I'm curious about that, the suitability modeler. Super cool. As you know, I'm a GIS fan myself, and I think that's a really cool application of that kind of software. I'm wondering, when you were talking about weighting the specific rasters, and you were talking about how it requires sort of a certain level of subjectivity, relying on knowledge and expertise. Could you give some examples of how you might rely on the subjective expertise of your team to decide those weights?
Sure. For example, I have a background in Karst and geology, not so much biodiversity. I'm interested in it, think it's great, but that's not my area of expertise. So within the rare and endangered species, that includes plants and animals. And so we put that in, we rated it really high because rare and endangered species should be ranked high for conservation value. But then you open it up and you have to individually classify and rank those criteria, which are a list of terrestrial species and aquatic species and other things that I don't know. So, that was a really good time for me to reach out to someone with that expertise and say, how should we rank these?
Yeah, totally.
Awesome. Thanks, Matt.
And then, Amy, if you don't mind, in the chat, could you also send your email just so that if people
Sure.
have questions afterwards, they can reach out? And then when you're done with that, I do see a question popped up into the Q&A chat.
Do you inject multiple dyes at the same location? If so, why would you do that? Okay, great question. We only inject one dye in each discrete location. But in one round, we may go into an area that has 3 separate hollows or drainage basins. And we may inject fluorescein into one basin, sulfurrhodamine B into another basin, and eosine OJ into another basin, and have all the springs downstream monitored with packets. So we would have, you're right, we would have no reason to put 2 dyes of different kinds in the same feature. There's no point of that. But we are able to see, did 2 of those drainages come to this packet? Did only 1 come? Did all 3 come? And so that's the real usefulness of using multiple dyes. And we're able to do like 12 dye injections in 3 days. They're 3 to 4 months apart, but we have 3 field days to do 12 dye injections instead of 12 days, instead of going 1 day and doing 1 dye injection.